Now, for the sake of illustration, we're going to do this exact same problem a second time, only this time we're going to interchange the order of integration. So last time we saw that we picked our base down in the xy plane, and the top was a function of z, that the z's went from that plane up until it hit this upper triangular plane. So we're going to do the same steps as we did before, only this time we're going to pick a different base, and so that means that we're going to have bounds on a different height. So let's, just for the sake of argument, we're going to pick a base that's over here in the xz plane. So I'm now sort of on my head, I'm tilting this, and I'm thinking that this is the bottom of my trapezoid, and the top of the trapezoid is going to be given as a function of y. So let's take a look about, let's do the same steps that we did before. Step 1, I'm going to set up the bounds for base. Bounds for base. Maybe these numbers don't exactly line up. That's okay. So in order to do that, I'm going to sketch a picture of what's going on. This time we're in the xz plane. I know that my z-intercept is up at 4, my x-intercept is down at 2, and I want to know what are the bounds on this triangular region. So I need to come up with an equation for this line that's the upper part of the function. In this case, the height is given by a function of z, or a function of x. My z's are each going to be 4 minus 1/2 x. No, minus 2x. Sorry. My slope is -2 here. I'm going down 4 and over 2. 4 divided by 2 is 2, so I get a -2 slope, and my z-intercept is 4. So that means that my bounds on z, they're going to go from z equals 0 up to where z equals this line. So I'll write them up here, that 0 is less than or equal to z, that's less than or equal to this line, which is 4 minus 2x. My x's, in this case, are going to be exactly the same as they were before. My x's are still going from 0 to 2 with this variable height in the z's. X's are between 0 and 2. So now that I have the bounds for the base, I'm going to have to come up with the bounds for the top. 2. Top. So the top in this case is exactly the same top that it was before. We're just thinking of it sideways. So in this case, I'm sort of thinking about, as I'm down in this region, how far over do I need to go before I hit the top of this tetrahedron? So in this case, the top is going to be in terms of my y variable. The equation for this plane is the same equation that we saw before, namely that 2x plus 2y plus z equals 4 is one possible equation for this plane, and I'm not going to worry about messing around with this. But in this case, we're going to have to solve it for y instead of solving it for z. So when I solve this for y, I get the fact that 2y is equal to 4 minus 2x minus z, or it means that y is equal to 2 minus x minus z over 2. So this is the upper bound for the top, and the lower bound is going to be down here at this shaded in base, and the base is where y equals 0. So it means that in this case, my bounds in y are going to go from 0 up until this plane, 2 minus x minus z over 2. So I have the bounds for the base, the bounds for the top, and now I can just set up my integral to integrate. Erase all this. And we have to be careful about the order of integration. Notice that we need to have our constants on the outside. So we have a triple integral over this function x plus y, d something, d something, d something. We know that our constant bounds are the x bounds, so I know that those should go on the outside. X is going from 0 to 2 dx. The next bound that has the next fewest number of variables is this z bound, because the z bound is only a function of x. So I can put the z bounds next. Z is going from 0 to 4 minus 2x. It's okay to have a variable in this bound that's an x, because I know I'm going to get rid of that x when I evaluate it at the constant terms next. But that means that our innermost integral in this case is going to be be our y's. So our y's are bounded from 0 to 2 minus x minus z over 2 dy. And if I wanted to, I could go through all the work. Sorry, this is an x. Turn that into an x. I could go through all the work of computing this integral, but I'm not going to. I already did a bunch of algebra, and I could have made mistakes with that algebra. So, yeah. Anyway, so this is how you set up triple integration with interchanging variables. Notice that we interchanged the order of the z's and the y's for this example, because the y's, our top and bottom, were now in the y's rather than in the z's, which is what they were previously. So for our final topic today, we're going to talk about finding volumes of three-dimensional objects using triple integration. And in this example, let's say that we're supposed to find the volume of the solid bounded by z equals 4 times e to the negative x, z equals 1, y equals 1, y equals 2, and x equals 0. So first, I'm going to sketch a picture of what, or a rough picture of what this looks like. So in this case, first I need to decide what does this function, the z equals 4 times e to the negative x look like? Well, this is my x plane, this is my y plane, this is my z plane. Recall that anytime I have a negative exponential function, it's going to be a function that starts out high and it gets lower and lower and lower. It has a vertical asymptote where x is equal to, or no, it's going to touch the axis where x is equal to 0, this becomes 1, and this value ends up being 4. So I just plugged in when x equals 0, e to the 0 is 1, so I'm up here at z equals 4. But as my x's increase, these values are going to get lower and lower and lower. Maybe I'll put my 4 up here just for the scaling of the picture. And it means that I have something that looks like this, curving downwards. And I'm also bounded by z equals 1. So I'm going to mark 1 on here. When z equals 1, that's a flat plane extending in every direction. And just for the sake of simplicity, I'm going to find out where does this flat plane of z equals 1 intersect. This intersection point is where 1 is equal to 4 times e to the negative x. I'm going to do some scratch work off to the side and say 1 is equal to 4 times e to the negative x. I divide by 4 and I say 1/4 is equal to e to the negative x. I'm going to take the natural log of both sides. The natural log of 1/4 is equal to negative x. So that means that in this case, x is equal to the negative natural log of 1/4. Or, recall, maybe this is an exponent rule that you don't necessarily remember, the fact that I can take coefficients and put them on the interior, meaning that this is equivalent to the natural log of 4. What is the natural log of 4? I don't know. It's a little bigger than 1 or something. I'm just going to label this here as the natural log of 4. So my z's are bounded above by this downward sloping thing and below by the z equals 1. My y values in this case are ranging from 1 to 2, and my x values are 0 is going to be this back plane back here. So let's go ahead and add in where our y's go from 1 to 2. In this case, that means that I'm up here where z equals 1. I'm going to go out as far as here. I'm going to go up to where z equals 4. And so this object, really, it sort of looks like a skateboard ramp. That picture totally makes sense to me, and I have no idea if it makes sense to you on the camera. Essentially, what I just drew here is that this base, it sort of works. It works for me visually. So the bottom of this shape, maybe I'll draw it over here so that we can see sort of if I draw it without all of the other lines in place. Oops. See, it's a skateboard ramp. Where the bottom down here is the plane where z equals 1. The back of this is the back where, in the zy plane where x equals 0. these sloping down places are the curves 4 times e to the negative x. And really what we want to do is we want to find the volume of this thing. How are we going to find the volume of this? We're going to use triple integration. The first step is the same steps that we saw before. I'm first going to decide on a base and find the bounds on the base. And in this case, I think the easiest base is the thing that sort of looks like the bottom of the skateboard. So the bounds on my base in this case are easy because this skateboard has a rectangular base. And it's a rectangular base where my y values are going from y equals 1 to y equals 2. And my x values are going from x equals 0, this back plane, all the way out until the intersection point that we already found. So our x values are going from 0 out until the natural log of 4. So those are the bounds on our base. Now we need to know what are the bounds on our height, or what's the top of this. The top of this in this case, right, is this curvy green skateboarding ramp. And that equation is given by what we've already been given. So we know that the top of our skateboard ramp is going to be where z is equal to 4 times e to the negative x. And the bottom of our skateboard ramp is the base of this, and that's, in this case, where z equals 1. So now we have all of the bounds, our bounds in y, our bounds in x, our bounds in z, and now we just need to set up some integration. The problem is, so far we've only talked about integrating over functions, right? So integrating over some density function. The trick to finding the volume, we've been finding volumes all along. Usually we've had some variable density. Now we don't have a variable density. Now the density, essentially, this is one way to think about it, is just 1. And I'll write this down up here, because this is something that I want you to remember of the takeaways from this video today. The volume of W in R3, so in this case, the skateboard ramp is RW, is given by the triple integral where my bounds are the bounds of W over 1 dV. This I'll put in a box. Meaning that I'm just going to take the triple integral, only this time my function is just going to be the constant 1. So what that means in this problem, if I'm plugging in what is my W, I've found the bounds of W right here. I'm going to integrate over 1, and I need to make sure that my dV, the differential with respect to volume, lines up with my x, y, and z variables correctly. So in this case, it's going to be a triple integral over 1. The z variable is going to go on the inside because it has an x in the term. So my z's are going from 1 to 4e to the negative x. My x values are going from 0 to the natural log of 4. And my y values are going from 1 to 2. And I'm integrating this with respect to z first, and then with respect to x, and then with respect to y. This triple integral expression is exactly the volume of this skateboard ramp. And the bounds came exactly from where we found the bounds to be by deciding what are the bounds on the top and bottom, and then what are the bounds on the base, which in this case was a rectangle. Thanks, that's all I have for triple integration.